Hello everyone, today we're going to be doing AP Precalculus Limacons. So Limacons are going to be the first polar functions that we'll be seeing in this AP course. And we're going to be looking at four different types of limacons today. The cardioid, the inner loop, the dimple, and the convex. Today we'll be using Desmos. So before we get into it, I'd like to acknowledge these two equations here. Similar to how y is a function of x, r is a function of theta. So it uses sine and cosine here, the same thing, and then we have a and b as our two values, but we'll take a look at those later and how they affect how the graph looks. So here at Desmos, I've already put in r equals cosine, negative cosine, sine, negative sine without a and b. These are the basic graphs that you should know on the polar plane. Just think of it in terms of the unit circle again. The cosine is on the x-axis, the horizontal axis. The sine is the vertical axis. And so in red, we have our positive cosine graph, which is going positive x. Our negative cosine, or blue, is going this way. Our green, positive sine at the vertical axis, it's up here, and our negative sine, negative on the vertical axis here. So these are the basic graphs that we're going to transform using a and b from the form earlier. Now, if you notice something about this form, a, the constant, is actually in the front. Usually it would be in the back, but in this case, it's actually easier for it to be in the front because we're going to be comparing a and b and see how they affect whether our limacon will be a cardioid, an inner loop, a dimple, or a convex. Let's start with the cardioid. Okay, so here we have our cardioid, and if you notice here, we can see that at 0, 0, both sides of the graph converge. This is one of the key features of a cardioid, is that it will converge perfectly at 0, 0, and it looks like a heart. And if you notice at our equation here, r equals 3 plus 3 cosine theta, we can see that a, our constant, and b, our coefficient, are the same. This is how you can recognize a cardioid. If a is equal to b, then it is a cardioid. Now we can graph another example. Let's say we do 5 plus 5 cosine theta. It will also converge at 0. It's still heart shaped. There's no loop, there's no dimple, which we'll get into in just a moment. Remember, for limacons, you can always think of the front face as to being the longer side, but we'll be able to see that more clearly with our next graph. Okay, so the next graph we'll be looking at is the inner loop limacon. Here we have our inner loop limacon. It's a bit different from the cardioid. Instead of converging at 0, it actually makes a small loop inside the little circle-like figure here. So let's take a look at the a and b values. First of all, our constant is smaller than our coefficient. So if a is less than b, then it is an inner loop graph. In addition to this, you also need to know where the diameters of the small loop and the big loop start and end. So if we look here, the small loop ends at 2. It has a diameter of 2. And then the big loop ends at 6. So in order to find the diameter of the small loop, all you have to do is b minus a equals diameter of the small loop. So b minus a, we have 4. 4 minus 2 equals 2, of course. And that would be the diameter of our small loop here. Now for the big loop, you would simply do a plus b. So a plus b in this case would equal 6. So that's why the diameter of the big loop is 6. Along with the cardioid, let's go write that down real quick on the Word document. Alright, so here's what we have so far. I wrote the things for a cardioid. We have if a equals b, then we have a cardioid, and the length, diameter of our cardioid will be double A or double B. I just didn't write double B because it's the same thing. For the inner loop, if A is less than B, then it is an inner loop limacon. And the diameter of the smaller loop will be B minus A, and the diameter of the big loop will be A plus B. This figure is kind of screwed up, so kind of ignore my bad drawing. Now before we move on to the dimple limacon, there's one last thing I want to mention for all these limacon equations in general. When you have a plus or minus sign here, you do not have to count it when you're doing a minus b or a plus b. I probably should have specified that. but it should be the absolute value of A and B when you're calculating the diameters. This simply points out the direction of your function, sine and cosine. Our sine is negative, so it would be pointing downwards. Our B value here would not be considered as -4, it would just be 4. Just keep that in mind as we move on to the dimple graph. Here we got the dimple graph, and if you notice, it's similar to cardioid, except it doesn't actually touch at 0. So what's happening here is the A value is actually bigger than the B value. So if A is greater than B, then the limacon is dimpled. So if you notice in our dimpled limacon, rather than converging at 0, it'll converge at a different point. In this case, for the equation that I've set up, it's going to converge at -1. Now, we can actually find this value using A and B again. It's simply B minus A, similar to finding the diameter of the inner loop from the inner loop limacon, and this will yield us a value of 3 minus 4, which is -1. And that makes sense because our value is -1 from here. You can also find the diameter of the dimpled limacon as a whole. Simply just add the two numbers, and that is where you'll find the diameter of the part of the limacon that is not in the dimpled section. It does not include this area. This also applies to the inner loop limacon from earlier. I might have forgotten to mention that. So now let's go update the Word document. I'll do that real quick. So here we have it. B minus A would equal to the diameter of the dimpled area, and then A plus B would equal the diameter of the area not in the dimpled section. Last but not least, let's move on to the convex. Okay, so here we have our convex limacon, and if you look closely, it's actually pretty similar to our dimpled limacon from earlier. So first, it falls under the rule A has to be less than B, so obviously it looks like kind of like a dimple here, but there's a catch to it, and I think that's the best way to think about it, and that is A has to be greater than or equal to 2B. So what this means is that the A value has to be 2 or more times greater than B for it to be a convex limacon, but visually you can see that at exactly 2 times the amount of B, instead of having a little dimple and going inwards, it'll actually just become like a straight line. So we can take a look at another example here, 12 minus 2 sine theta. You'll notice that it's almost a full circle, but not quite. No matter how much this value increases, it'll never become a full circle, never. As it approaches infinity, it will attempt to, it'll almost reach a full circle, but theoretically it never will. So yeah, that's all you really need to know for convex limacons. More or less just a more far out version of the dimpled limacon from earlier. Oh, and one more thing before we move on. In order to find the diameter of the convex area, we simply have to do the same operation. B minus the A, 4 minus 8, which is -4, which makes sense. And then 8 plus 4, A plus B, would equal our diameter for the bigger side of the convex limacon. So yeah, that's really it. Nothing too crazy, but I just thought it'd be interesting to share. So let's write this down in our Word document here. So yeah, that wraps it up for this video. We covered cardioids, the inner loop, the dimple, and the convex limacon. Just for a quick summary, let's just go over it. So first of all, we have our two equations. We have our constant A and our coefficient B, and then sine and cosine. The cardioid is simply a graph where the points solidly converge at 0. It's heart-shaped, and A and B are the same. And then for the inner loop, here we have a small loop inside. The diameter of the small loop is equal to B minus A, and the diameter of the rest of the inner loop limacon is A plus B, kind of poorly represented here. Sorry about that. Moving on, we have our dimple. If A is greater than B, then it is a dimple graph. B minus A represents our diameter of the dimpled area. A plus B, same thing, diameter of the bigger loop. Same thing for the convex, except the A value has to be greater than or equal to 2 times the value of B. So yeah, this is just an introduction to our graphs here. I just thought this would be an interesting video to make. So I hope you learned something and took away something from this video. I'll see you next time.